In this example, we'll be looking at how to apply the formula for the combined gas law. So the combined gas law takes all the relationships that we've learned in Boyle's law, Charles' law, and Gay-Lussac's law and puts them together such that none of pressure, volume, or temperature have to be constant. So it makes the situations a little bit more realistic. The combined gas law is given by P1V1 over T1 equals P2V2 over T2. And as we go through this question, we'll be able to discuss why we knew to use that equation. So the question tells us that Mark's hot air balloon trip takes him to an altitude of 7,000 meters. At that height, the atmospheric pressure drops to 300 millimeters of mercury and the temperature is negative 33 degrees Celsius. Suppose Mark carries a small balloon originally filled with 1 liter of helium at a pressure of 760 millimeters of mercury and a temperature of 27 degrees Celsius. What would be its volume at 7,000 meters? So the key thing there is to recognize that 7,000 meters is irrelevant information. The height is not given anywhere in this equation, so it's a distractor. It just tells you what the initial, it's just a way to signal to you what the initial and what the final situations look like. So that means we will go through the process of making a data list, making sure that we identify what we know and what we don't know. So the initial pressure, and we can know which one that is because it says, suppose Mark carries a small balloon originally filled with 1 liter of helium at a pressure of 760 millimeters of mercury. So that phrase originally can signal to you that it's initial. So 760 millimeters of mercury is the initial pressure. The initial volume is 1 liter. The initial temperature is 27 degrees Celsius, which we're going to have to convert into Kelvin. The final pressure, once Mark gets up to 7,000 meters in altitude in the hot air balloon, the final pressure is 300 millimeters of mercury. The final volume is our unknown. What would be its volume at 7,000 meters? That's what we're asked for. And then the final temperature is negative 33 degrees Celsius, which we'll have to convert into Kelvin. So we'll do our temperature conversions first. We know that when we're going from Celsius to Kelvin, we add 273.15. So that'll give us 240.15 Kelvin for the final temperature, and the initial temperature is going to be 300.15 Kelvin. Alright, so we have all of our information and we have identified our unknown. So now we're just going to have to rearrange this equation to solve for the unknown. So our first step that we can do is we can multiply both sides of the equation by T2, and here's where the algebra starts to get a bit more complex. We can multiply both sides by T2 so that the final temperature cancels out on the right side of the equation, and that is going to give us P1 times V1 times T2 over T1 equals P2 times V2. We still want the final volume, or V2, on its own. So to achieve that, we can divide both sides by the final pressure. And then we'll know that V2 is equal to P1 times V1 times T2 over T1 times P2. If there are any questions about the algebra involved there and why it turns out that way, please just let me know. So now that we've isolated the variable we want to solve for on its own, we just need to sub in all of our information. So P1 is 760 millimeters of mercury. The initial volume is 1 liter. The final temperature is 240.15 degrees Kelvin, and that's all divided by the initial temperature of 300.15 Kelvin multiplied by the final pressure of 300 millimeters of mercury. Something to keep in mind here is that when you're dealing with this many units, it can seem complex. And you might be wondering, oh, well, why are we using millimeters of mercury as a pressure unit? You know, we haven't seen that a lot. The units are all going to cancel out to give you your final unit. So just doing that quickly, looking at what units will cancel out, doing that algebra on the units tells us that our final answer will be in units of liters, which is a unit of volume. So that's another way we can check to make sure we've set up the algebra correctly. So when you enter all of that into your calculator, and you'll get a final answer, you get approximately 2.03 liters. So therefore, the final volume at 7,000 meters is 2.03 liters. And then conceptually, just make a note of the temperature effect here. So the temperature effect, because the final temperature was much colder than the initial temperature, ends up being basically overpowered by the radical drop in pressure to ultimately double the volume of the balloon. So normally you would expect that if you're just looking at volume and temperature, that a lower temperature means a lower volume. But because the pressure difference was so strong here, it basically totally overcame the temperature difference and allowed us to still have a larger final volume. So again, to recap, we went through our question, we extracted all of the relevant information into a data list, we identified the equation that we're going to use to solve the problem, we performed algebra to manipulate the expression to isolate the variable that we want to solve for, we subbed in all of our information, and then we got a final answer of 2.03 liters.